Hey there, man, Alejandro, and welcome back for day 10 of me doing the Advent of Code December 2024 challenge. So today we get the problem, Hoof, eat. You all arrive at a lava production facility on a floating island in the level sky. As others begin to search the massive industrial complex, you feel a small nose boop your leg and look down to discover a reindeer wearing a hard hat. The reindeer is holding a book titled Lava Island Hiking Guide. However, when you open the book, you discover that most of it seems to have been scorched by lava. As you're about to ask how you can help, the reindeer brings you a blank topographic map of the surrounding area, your puzzle input, and looks up at you excitedly. Perhaps you can fill in the missing hiking trails? The topographic map indicates the height at each position using a scale from 0, lowest, to 9, highest. For example, 0, 1, 2, 3, 1, 2, 3, 4, 8, 7, 6, 5, 9, 8, 7, 6. Based on unscorched scraps of the book, you determine that a good hiking trail is as long as possible and has an even, gradual uphill slope. For all practical purposes, this means that a hiking trail is any path that starts at height 0, ends at height 9, and always increases by a height of exactly 1 at each step. Hiking trails never include diagonal steps, only up, down, left, or right, from the perspective of the map. Interesting. Starts at height 0, ends at height 9, and always increases the height exactly 1 at each step. Hiking trails never include diagonal steps, only up. Okay. You look up from the map and notice that the reindeer has helpfully begun to construct a small pile of pencils, markers, rulers, compasses, stickers, and other equipment you might need to update the map with hiking trails. A trailhead is any position that starts one or more hiking trails. Here, these positions will always have height 0. Assembling more fragments of pages, you establish that a trailhead score is the number of 9 height positions reachable from that trailhead via a hiking trail. In the above example, the single trailhead in the top left corner has a score of 1 because it can reach a single 9, the one in the bottom left. This trailhead has a score of 2. I see. The positions marked dot are impassable tiles. To simplify these examples, they do not appear on your actual topographic map. Interesting. So let's reread this. A trailhead is any position that starts one or more hiking trails. Here, these positions will always have a height of 0. I see. So for example, here there's a 0. Can there be multiple zeros? Always have a height. Okay. Assembling more fragments of pages, you establish that a trailhead score. So is it basically like you can only go up by 1? And so it's like, like you can go from 1 to 2, 3 to 4, 5, 6, 7, 8, 9. So that's one path. 1, 1. You cannot go to the 8. So you can go to the 2, 3, 4. So is that what's going on? These positions, okay, assembling more fragments of these pages, you establish that the trailhead score is the number of 9 height positions reachable from that trailhead via hiking trail. Oh, a trailhead score is the number of 9 height positions reachable from that. Okay, so basically from the zeros, BFS and or even DFS, whatever, and essentially just mark the number of 9s that you visit along the way. Okay, in the above example, the single trailhead in the top left corner has a score of 1 because it can reach a single 9, the one in the bottom left, right? And so based on as long as possible, has an even gradual uphill slope. For all practice, this means that a hiking trail is any path that starts at a height 0, ends at a height 9, and always increases by a height of exactly 1 at each step. So you have to increase. You cannot decrease. Because we had a problem before where it's like, you could like take an even number of steps and you go like 1, 2, 3, 4, 5 in terms of time in the daily lead code challenge. So here's like, okay, you can only increase, right? So you can essentially only visit neighbors that have a value of your current value plus 1. Okay. Which actually means that we don't even need a visited set, right? We just keep going until we're done. Right? Because we might be able to, revisit it too. Basically, maybe we can mark the 9s inside of a set. And that way we can essentially see how many 9s we mark. Right? Yeah. Let's do that. Let's put the 9s that we find inside of a set. But like, yeah, we should explore this too as well. This too. Yeah, it's essentially BFS. But the point is that since you can only go up in height, you never have to worry about cycles, right? Okay, so that's basically the point. The trailhead has a score of 2. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, sure. The positions are impassable tiles. For this example, they do not appear on your actual top. Okay, this trailhead has a score of 4 because 9 is reachable via hiking trail except the one immediately to the left of the trailhead. Yeah, makes sense. This topographic map contains two trailheads, the trailhead at the top with a score of 1 and the trailhead at the bottom with a score of 2. Sure? This larger example has 9 trailheads. Consider the trailheads in reading order. They are scores, yeah. Adding these scores together. Okay, so the sum of the trailheads. Okay, easy. Okay, so I understand the problem. I understand it now. You know how they say it in the meme? Okay, anyways. Okay, so let's come in here. Let's set this up in GitHub Desktop, Visual Studio Code, as we do in every single day. Let's come in here. Let's close out these guys over here. There we go. Put this over here. Put a 10 here. This is day 10. So now we're in the two-figure digits officially, which feels very nice. Here we'll do data.txt. We'll put in that boy nice in there, right in there. Then here we'll do in a nice little test data.txt. And here it's like, okay, here's the one that we expect the value of 36 in. So we can just test with that. And here we can do a part1.py as well as a, we'll add part 2 when we need it, right? Okay, so here we'll do it as always. So use test data is equal to true. So here we'll say file name equals /test data.txt. If use test data, else /data.txt. With open file name in read mode as file, filed.read lines. This lines equals line.strip for line in file.read lines. Okay. Here we'll say C for C in. So here we'll say grid, print for line in grid, print line. Right, so here let's cd /10 python 3 part1.py. Okay, so here we have our 890. Here we'll make this an int digit for digit in line. There we go. So yeah, so now we have 8901, and then there we go. Perfect. Okay, and now we'll come up with a very simple solution. We'll say for I in range, so here we'll say m comma n is equal to length of grid as well as length of grid of 0. For I in range m, for j in range n, we'll just say num is equal to grid of ij. If num doesn't equal 0, and continue, right? Otherwise, count number of 9s reachable from this 0. So here we'll say res equal to 0, res plus or equal to BFS with our current grid and our I and j. Right? So here we'll do a def BFS, grid I and j, and this will be very simple, right? We can even DFS, right? This is equal to a set, 9 positions, goal positions, i.e. positions, i.e. I comma j positions of 9s reached. Original I comma j. So here we'll say assert grid of I j is equal to 0. Okay, goal positions is equal to set. So yes, so these are the 9s. Then we'll say, okay, here we'll have a def inbounds function, I comma j, and here we'll say return 0 less or equal to I less than m, and 0 less or equal to j less than n. Yeah, so we can refactor this to m comma n. You know what? There we go. This is an m. This is an n. Make this the m. We'll make this an n. That way they're known constants. Goal positions is equal to set. And yeah, okay. Here we'll say directions is equal to 0, -1, 0, 1, as well as 1, -1, 0, as well as 1, 0. Right? Negative, positive, negative, positive. Okay, cool. For dx, dy in directions, stack equals this. Yeah, is equal to this with I, j. While length of stack is greater than 0, we'll say x, y equals stack.pop. Right, we'll just do DFS, but in this case it doesn't matter. And we don't even need a visit set because we can only go to neighbors that have a higher value, so we don't even have to worry about cycles here, so we don't even need to check, any visit sets and so on. It's just that whenever we reach 9, we'll add that, right? So if grid of xy is equal to 9, then def goal state is equal to 9, start state is equal to 0, right? If none doesn't equal start state, grid of ij DFS print f string answer with res. Okay, I don't know why it's complaining about this. Oh, it's because of this. So yeah, so if this is equal to goal state, then we'll do goal positions dot add x, y. Okay, and we'll say for dx, dy in directions, if new x, new y equals to x plus dx, y plus dy. If grid of new x, new y equals to grid of x, y plus 1, if in bounds new x, new y, and it's 1 more than the previous value. So from x, y, we can only increase our height by 1, and we can only go up, down, left, right, which is our directions. Then we'll do stack dot append new x, new y. Right? And then here, we'll return length of goal positions. Right? DFS grid of I. Okay, so right now let's run this. Okay, so the answer was 36. Okay, so we already have it. And so yeah, okay, so we already have this. Okay, so let's get rid of this. Let's put in a false here. Python 3, 514. Let's put this guy in here. That's the right answer. You're 1 gold star closer to finding the chief historian. Continue to part 2. Okay, feels very nice and good. All right, part 2. The ranger spends a few minutes reviewing your hiking trail map before realizing something, disappearing for a few minutes, and finally returning with yet another slightly charred piece of paper. The paper describes a second way to measure a trailhead called its rating. A trailhead's rating is a number of distinct hiking trails which begin at that trailhead. For example, 0, so yeah, you can go this path, okay. The above map has a single trailhead. Its rating is 3 because you are exactly 3 distinct hiking trails which begin at that position. So it's just the number of original neighbors. Is that literally it? That's even easier than the previous problem. You just look at you don't even DFS, right? Bruh, wait. The above example has a single trailhead. Its rating is 3 because there are exactly 3 distinct hiking trails which began at that position. Okay, here's a map containing a single trailhead with rating 13. So there's 1, 2, 3. Oh, no. So is it unique paths? Not just unique starting paths. Number of distinct hiking trails. So one that is able to reach a 9. Yeah. Wait. Oh no, essentially whenever you reach a 9, then that was a new way you reached it. Okay. Here's a map containing the trailhead with rating 13. Yeah. With rating 227. Okay, so first of all, let me copy over my code from part 1 and bring this over to part2.py. And here essentially, I'm going to make one modification. Unique paths equals 0. Here we'll say unique paths plus or equal to 1. And here, return unique paths count. So here we'll put in a true here. Part2.py, we get 81. Is 81 with it? Okay, so that's literally just it. Okay, so let's put this back to false. 1162, is that the right answer? That's the right answer. You're 1 gold star closer to finding the chief historian. You have completed day 10. You can share this victory or return to your advent calendar. Okay, nice. Ooh, what is this blue line stuff? Okay. Is this like a bow? No, but why would there be a bow for Christmas time? Also, okay, wait. What's going on over here? Okay, we're getting into the sus zone now. Okay, I still have no clue what this is. I hope I figure out what this is. What is this? What is that? It's just green. This, what is it? Like a row? I don't, okay. There's gonna be, there's some stuff appearing now, you know? Like it's, with time we will tell, right? I don't know if this is Santa Claus over here. There's some blue action going on over here, which is very, very interesting. Huh, maybe this is like a mini Christmas tree right here? Maybe this is the Grinch, but it's just like a mini Grinch. And this is his just little face right over there. Huh, I wonder. Okay, but nevertheless, as always, you know what? Let me just go pick this up. So, I don't have my advent calendar with me today, but I was smart enough. So here I'm at my friend's place because we were doing a board game night. And I was smart enough to bring a Ferrero Rocher from my advent calendar. So in case you are eating an advent calendar chocolate with me every single day, I still came prepared so that we could do that together. So here's a Ferrero Rocher. If you're having one with me, then here, cheers to you, my friends, and let's go. Oh yeah. Oh, Ferrero Rocher always hits so nice. I'll have to stop after December because I think I had a nosebleed during the Daily Lico challenge today, and I think it's from all the sugar I'm eating. Maybe not just Ferrero Rochers and so on. Although I mostly eat okay, I also ate like a pound and a half of ground beef for like a few days in a row. So maybe that has to contribute a little bit with it. But usually I don't have the highest tolerance, I guess, in the world for sugar. I've never tested myself for something like diabetes or anything like that, but which I probably don't have. But yeah, it's sometimes weird. Okay, that's completely irrelevant. Yeah, this was a nice and simple, succinct one. So I mean, as always, I can do a quick review of how I was able to solve this problem. So we can go into like day 10. Essentially, this is the way I solve this is basically a graph. First of all, as always, I'll just make sure that I commit my solutions here onto GitHub, which, by the way, description down in the link in the description down below in case you're curious about all my solutions and so on. It is in my GitHub repository, which I link in the description down below. But essentially, otherwise, here the input is basically a graph, and the graph is essentially, you know, just a bunch of these numbers, and essentially it's like what it tells you is like, okay, you can only start from zeros, and from zeros what you're interested in is reaching nines, and the only thing you're able to do is you essentially have neighbors, which are your up, right, down, left neighbors, and for those neighbors you can only go to ones that would increase your height by 1. So like, for example, from this 0, you can only go to things that are 0 plus 1, so a 1. So we look up, well, up is out of bounds, so disregard it. We look right. Is right a 1? It is indeed, so that could be a neighbor that we consider. Is down a 1? It is indeed, so we consider it. What about the left? Well, it's out of the border, so we don't consider it, right? And so then we continue from these guys. From this guy, is the up case 1 plus 1 equals 2, so we're looking for 2s. This is not, right? This is what I mean earlier by the... It's not, it must be acyclic, so that's why I didn't, you know, keep track of a visited set and not just the DFS and whatever, because of the fact that, hey, since we only want to care neighbors that, you know, have a value plus 1 and their only value is 0 to 9, we know that we can never go back in a path, right? So that was kind of the nice unique thing. And so from this one, it's like, okay, we know that the top one will always be false because that's where we came from, and, you know, we got here because it was 0 plus 1, so this cannot be, you know, 1 plus 1. It cannot be the case. So this 0 is not a 2, so we ignore it. Okay, this 2 is indeed valid, so we consider it. Here, this 8 is invalid because it's not a 2. And then in the left case, we're out of bounds, so we can't consider it, right? So like from that point, we'd only consider this. From this, you know, we look at its neighbor, it can only consider 2s. Up is out of bounds, left is nonsense. You know, this 2 works and this 2 works, and so it's like we'd explore from these 2s. These 2s can only reach 3, so this is nonsense. Nothing up top. Oh, but it can reach this 3. Oh, and it can reach this 3 over here. This 2 as well, I can reach this 3 over here. But up it cannot go, left it cannot go, 7 it cannot go. So the point is you can only, you know, go by 1, right? And the point is like you treat it like a graph. And essentially, you have 4 neighbors, up, down, left, and right. And for each of the neighbors, you ask yourself, okay, first of all, is it in bounds? And if it is in bounds, is it exactly my node's value plus 1, right? So like from 0, it's like, okay, right is not out of bounds. It's a 1. Is it equal to 0 plus 1? Well, yes, it is. It's equal to 1. So I can go to that, right? So that's essentially all I did in my code. So here I can come into part 1. I essentially have a DFS function. So what I do is essentially I read the input as a grid. And, you know, for every single index I in the rows, for every single index j in the columns, I said like, okay, if grid of ij doesn't equal 0, so that's the start date is just a constant that I said 0, then I'm just going to continue the for loop. Otherwise, okay, if it's a 0, that means I want to explore as many nines as I possibly can, right? The point is essentially for each one, you want to know how many rating nines you can reach from. So essentially what I did is like, okay, DFS from position ij in the grid, right? And so DFS, all it looks like is like, okay, I use my stack. I'm going to keep track of a set of the positions of the nines that I was able to reach, right? Because again, all I want for each of them is, I forgot what the term they used, a trailhead and so on, or the score of a trailhead. Essentially, starting from a node 0, you want to know how many unique nines can it reach from that 0, right? And so here is just like, okay, let's keep track of a hash set of, you know, the 9 positions that it's able to reach, which is initially empty. Here we put in our stack like in a regular DFS, starting from ij because that's where we're starting, asserting that it's equal to 0, right? Or, you know, better yet, I could do like, you know, is equal to the start state. But yeah, it's fine. We must start from 0 is the point. Then it's like, okay, while length of the stack is greater than 0, you know, pop from the stack. And it's like, okay, you know, if the value is a 9, that means we would just reach a 9, add that position to our goal positions hash set, right? Whenever we reach a 9, we should mark that as visited. Then it's like, okay, from the current node, we're going to say, okay, for each direction, up, down, left, and right, we're going to compute the new position and say, okay, if that position is in bounds, and it happens to be that the value at that position is exactly 1 more than the position we came from, right? We came from x and y, and now we're at new x, new y, right? Which is x plus dx, y plus dy for each of these, you know, deltas. Like, you know, this one of them is like going up, one of them is going down, left and right, pretty much. And then for them, it's like, okay, if the new values position is exactly 1 more from the previous, and it's in bounds, then we can say, okay, we can continue exploration from that node, right? So essentially, it's like it is a valid neighbor if and only if it is in bounds, and you know it's 1 more than the position we came from, right? In that case, we append it from the stack, which will continue searching stuff. And at any point, you know, if we reach another 9, then it's like, okay, add that into our hash set, and that's like, okay, from this position ij, which was a 0, we return the, you know, the goal, the number, the length of the hash set which represents the positions of the 9s that we visited, which is essentially the score of that trailhead, right? Inside of this hash set, we have, the positions of, the 9s that, the unique positions of the 9s that we were able to reach from the original IJ that had a 0. And so when we return the length of that, that's essentially the number of unique 9s we were able to reach, which is the score of the trailhead. And so we literally do this where it's like res is equal to 0 for every single index in the grid. If it is a 0, we're going to append to our res, the score of that trailhead, right? We're going to DFS from IJ, count the number of unique 9s that's reachable from that guy, and append that to our result, right? For every single index in the grid that happens to be a 0, right? So for every single index, if it's not a 0, then it's just say continue in the for loop. Otherwise, I say, okay, augment our res value with the number of 9s that are reachable from this 0, right? And at the very end, I return my answer. Now, part 2, the only difference is that it's like, okay, we don't want just the number of unique 9s. We want the number of paths that lead to a 9, which is basically just asking, like, how many times do you reach a 9? Since you can only go up by 1, there's no cycles in this graph. So the number of times you reach a 9 means that every time you reach a 9, it was a unique path that reached you to that 9, right? Another unique path might reach that 9, another unique path might reach that 9. But the point is, like, in part 1, we only cared, about the unique number of 9s. If anything, part 1 was a little bit harder because we kept track of a hash set of, the 9 positions that we reached. So that way, it's like we keep track of only the unique amount of 9s that we reach in total. But otherwise, all I did in part 2 is like, okay, instead of using a hash set, let's straight up keep a counter variable where whenever we find a position that is a 9, instead of adding its position to our hash set, that way we only keep the unique number of 9s, we're going to augment our unique path variable by 1. Why? Because every time we reach a 9, since this graph is acyclic and you have only at most 4 neighbors and so on, it's just like the grid that it's set up, every time we reach a 9, we must have reached it via some unique path, right? Like each path will either reach a 9 or not, right? So the number of times we reach a 9 is, and by the way, exactly 0 or once, right? So, exactly once, because, from 9, you cannot go up to a 10 or whatever and so on, right? So each path either visits 0 9s or it visits 1 9. Right? And so obviously we'll search all the paths that are like starting from the trailhead. And so every single time that we hit a 9, it must have been this is a new unique path that just hit that 9, which will terminate at that 9, because from 9, all the neighbors, none of them will have a value greater than 9, so you can't explore, and there you go, blah, blah, blah. So each unique path will either hit 0 9s or 1 9. So essentially, the number of 9s that are hit in total is the number of unique paths that reach a 9 in the end of the day, right? So instead of adding it to a hash set where then we return the length of the hash set, every time we see a 9, we say that's a direct hit. That's one more unique path that reaches me to a 9. And so at the end of the day, we just return, the number of unique paths. Same exact code otherwise. We just return res. It works like a charm. There you go. Bada bing, bada boom. And that's pretty much it. And so that's how I was able to solve the problems for part 1 and part 2. This was a nice, short and simple one, so feels good. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.